Additive manufacturing lecture number 2, and this is for last week. I'll continue that the others for this week in the next couple of days. So in the last class we talked a little bit about what are the different additive manufacturing techniques, concepts, and some common examples, some introduction. And in the current lecture, we will continue that introduction and give you additional details about the different additive manufacturing techniques that you can observe in the real world. So, how do you define, or how does the American Society for Testing Materials define additive manufacturing? So this is what they say. Unfortunately, this particular definition has been withdrawn, but I think we can still continue to use that. And this was the first attempt at codifying the additive manufacturing process. It's a good definition to know. And what it says is that essentially all the additive manufacturing processes can be divided into 7 different types. So in this case, there are several terms that are used to provide a structure for grouping different current and future additive manufacturing technologies. These are useful for, especially for educational and standards development purposes, and you can classify which machine type will share processing similarities or manufacturing similarities. And they enable one to discuss a category of machines rather than needing to explain a wide variety of commercial variations of a process methodology. So the first one is the vat polymerization. And this is one of the oldest technologies developed. It's called stereolithography. So essentially what you are taking a container of liquid polymer, photopolymer resin, which is an acrylate type of a resin, and if you expose that to ultraviolet light, not over the entire vat, but you specifically draw a line from a laser which produces ultraviolet light. You can cure or harden the resin where it is exposed to that. And then if you are moving this whole container on top of a platform, then you are essentially meeting the needs of a fixtureless platform. And after you make one layer, the whole component or the platform goes down by a small distance and more resin comes on top. So now you can shine laser on the next layer of the material. And you can control the layer thickness by controlling the viscosity of the resin system. So you can create different layers and build up the whole part layer by layer. So essentially, this shows on the right hand side on the top is a schematic of the whole manufacturing process. You have a laser beam being created by a helium neodymium or helium cadmium type of a laser, and you have a fixtureless platform and you build the first layer. This goes down by one small distance, then more resin is flows on top, and then when you shine the laser again on top of that laser layer where you need the solid areas, then it hardens and so on. So you build the whole part like that, and you can have overhangs, undercuts. It doesn't matter because you don't need any support material at all. some machines use a blade which moves between the layers to provide a smooth resin base to build the next layer on. And after completion, the whole vat is drained of the resin, and you can remove the whole object after that. So this shows an example of a part. So this is a pretty complicated shape, and you can build that kind of a part from this kind of a process. The what are the technical information that you can that you can get from this process? The SLA process has a very high level of accuracy and extremely good finish. In the beginning, the layer thicknesses used to be of the order of half a millimeter at the most, but now you don't need that much. You can probably have a couple of 100 microns or maybe even 50 microns. So by building it layer by layer under such small numbers, you can get extremely small and accurate parts. It can be achieved using a single laser and optics, and the blades or recoating blades pass over the previous layer to ensure that there are no defects in the resin for the construction of the next layer, because this resin is being used over and over again, so that there are no and you use this blade such that there are no defects or no impurities in the resin, so that it does not mess up the part that is being built. Typical layer thicknesses are of the order of 25 microns to 500 microns. So if you know that the wall thicknesses are pretty uniform, then you don't need to get such a small layer thickness. You can get you can use much larger layer thicknesses. The parts must be removed from the resin, and the excess resin is fully drained from the vat. If there are supports, then you can remove them using a knife or sharp device. But you should make sure that you are not contaminating the resin with appropriate safety precautions, because in case the laser just shines even by mistake on a free part of the resin, then it hardens, and that hard layers are left behind in the resin vat. So you need that kind of a hard piece coming on top of the part that is being built. If that happens, then the whole part is scrapped. And the after you make the part, you can use different things like different cleaning techniques, like you have to have an alcohol rinse followed by a water rinse. The problem, especially if you have very small the layer thicknesses, is that the processing is very, very lengthy. So even a part similar to the one that you saw in the earlier slide, it can take you as much as 15-20 hours and things like that. So it is a continuous process. Anything can go wrong. So you have to make sure that, you don't need to be constantly watching it, but you have to come by and make sure that the process is running properly after every couple of hours or so. You can have the part dried naturally or by using an air hose, and UV light can be used for a final post-cure process to ensure a high quality object. But even though this is the oldest process, it has got certain issues, especially health related issues with it, because these are acrylate resins, and you need to follow and make sure that you are adopting the safety data sheet for this material. Nowadays, especially the new SDS standards have to meet something called the globally harmonized system of the classification and labeling of chemical materials. And biggest problem I see is that, I mean, this is my personal opinion, okay? Um, Most SLA resins say in the classification system that these resins are proprietary. So you really don't know what exactly is in the resin. And sometimes you don't have any lids on the vats, although some printer models have cabinets that enclose the vat and laser as a laser fires into it. So if there are any fumes trapped inside the cabinet, when you open it, it will be released when the lid is open to retrieve the final printed object. So what is the problem? These exposure limits are based on OSHA exposure limits that are approximately 40 years old. And you have, I mean, nowadays, especially the new systems are that you have what is called the permissible exposure limits, that is actually going down, which is the acceptable amount of a substance in the air, a form of protection, and so which means which will need a form of protection from hazardous chemicals. So you need some kind of a protective gear when you are using this kind of an equipment. But if you go into a rapid prototyping or a 3D printing or additive manufacturing shop, you may not always find this present. So people working there are constantly exposed to these acrylate resins. And the other thing is that these are methacrylic ester monomers. Um, OSHA's permissible exposure limit is 100 parts per million, but the industrial hygienist recommended PEL is 50 parts per million. What is happening now? 3D printing has become so common, it is there in high schools, job shops, etc. etc. So people operating these machines may not always understand or may not always use the right kind of protective gear, because even middle school kids are using this technology. So you have a number of issues with that. So you got to be careful when you are using these pieces of equipment and resin systems. So what are some examples of machines and material examples? So if you look at, I mean, this one is about a year old, but I think these machines are still there. So 3D Systems is the biggest manufacturer of stereolithography equipment, and this is the largest machine, one of the largest machines made by 3D Systems. It can make a part as heavy as 450 kilos or about 1,000 pounds. And it has a build area of um, 150 centimeters by 75 centimeters by 55 centimeters. So pretty large equipment. And um, the polymer used in this one is an UV curable photopolymer resin. It's again a methacrylate resin. And the resin systems are uh, proprietary to 3D systems. So, what are some advantages of stereolithography? The first one and the most important one is that it is still one of the techniques that is used in the maximum number of applications, maximum number of machines are out there. Of course, if you ask somebody from statistics, they will claim that their machines have sold the maximum number. But I think that stereolithography has a very high level of accuracy and good finish compared to the next technique that we will be seeing. It is relatively a quick process, and it can typically build large components. But what are some of the disadvantages? It is relatively expensive. It has got lengthy post-processing time and removal from the resin. It has limited material use of photoresins. It often requires support structures and post-curing for parts to be strong enough for structural use. So if you click on this particular YouTube, I think it is still there. You can find an example of this process. Okay. The next one is the material jetting process. It is a process in which droplets of bill material are selectively deposited. The examples are photopolymer and wax-based process. There is some overlap between stereolithography and material jetting, but of course the resin systems that are used in material jetting are much less dangerous compared to the stereolithography resins. So this is very similar to two-dimensional inkjet printer. Um, so there are even techniques that people are doing, like they expose paper to some kind of a resin system that gets reacted with the paper and make it into a hard material. And the material is deposited from a nozzle which moves horizontally across a build platform. The material layers are then cured or hardened using UV light. And the nozzle can be part of a inkjet printer head that you can buy from the Staples or somebody like that, and you have to remove the inkjet fluid and fill your own fluid that is used to react with the material. Polymers and waxes are also suitable and commonly used materials due to their viscous nature and ability to form drops. So this is an example of that, of an piece of equipment. And what are the different steps? The different steps are the print head is positioned above the build platform and the droplets are deposited. Then it builds the first layer, then it goes down, you build further layers on top of the previous layers. The layers are allowed to cool and hardened using UV light, and the post-processing includes the removal of support material. So there are more details here. I won't go over every one of them. Essentially, you have to have post-processing just like the stereolithography process. And here is an example of that machine. And one of the common suppliers of this equipment is a company called Object. I would suggest that you should go and look up these pieces of equipment and see what kind of materials can be built using this kind of a process. And what are some of the advantages? The advantages, again, high accuracy. You can have multiple material parts and colors under one process. What are some of the disadvantages? Support material is often required, and but the disadvantages is that materials are limited and only polymers and waxes can be used. And here is an example of that in the on YouTube. You can find this and look it up. So I will stop this part of the lecture here and continue that in the next lecture.